Some reactions happen in the blink of an eye, like fireworks lighting up the sky, while others take years, like a car, slowly rusting away. Both are chemical reactions, but they have very different speeds. What makes one reaction sprint ahead while another crawls? Let's discover what controls the speed of chemical reactions. This is Real Chem. Speed is something we instinctively understand. Whether it's cruising along a highway or sprinting to win a race, we can measure how fast things happen. But what about in chemical reactions? In chemistry, speed is all about how quickly reactants turn into products. To figure this out, we need to measure the rate of change over time, just like tracking a runner's pace during a race. Today, we'll explore how to quantify reaction rates and see why some reactions are lightning fast while others crawl forward. Jamaican sprinter Usain Bolt set the 100-meter world record, flying down the track like a rocket. Meanwhile, here's me, just trying my best to keep moving. Clearly he is faster, but how much faster? Let's quantify it. Here's a plot of his position versus time. The y-axis is his distance in meters from the finish line, and the x-axis is his time in seconds. Let's say, for simplicity, his speed is continuous from start to finish, as shown by this line. He does the entire 100 meters in 9.58 seconds. To determine his average speed, the math here is simple. The change in the y-axis is 100 meters, divided by the change in the x-axis, 9.58 seconds. This gives the speed of 10.4 meters per second, which is the slope of the line. Now let's look at my run. Since I slow down as I run, don't judge. We need to use the slope of the tangent line at any given point to measure my speed right at that moment. Right around here, I went from 2.3 meters in 1 second, so the slope of the line, or more precisely, the tangent to the curve, is 2.3 meters per second. This is my speed right at that moment. Later in the run, say by 45 seconds, the rate has reduced again. The slope is less steep. When I run, I change my position and my speed is related to how fast my position changes. But what changes in a chemical reaction? Let's look at a class of chemical reactions where two things, let's call them A and B, combine to form a dimer that we will call AB. Let's say that we mix some A and some B together and watch this reaction occur. Every so often, an A and B may collide and form the AB dimer. If we take a snapshot 10 seconds later, we may see this. A and B have formed the product AB. Sometime later, we see that more AB appears. So what is changing here? It is the amount of reactants and products. The amount of A and B is decreasing with time, while the amount of AB is increasing. We typically express the amount of the reactants and products as their concentration. How many A's and B's do we have in a certain unit of volume? How can we determine the speed or rate of this reaction? Remember, to get the speed of our runners, we plotted the thing that was changing, their position versus time. Here, we also plot the thing that was changing, concentration of the species A on the y-axis versus time on the x-axis. Let's take a look at how the concentration of A changes over time. The speed or rate of the reaction is the slope of the tangent to this line. The slope of the tangent near the start gives us 0.2 molar per second. But this slows down as the reaction progresses. Down here, the tangent line has a slope of only 0.1 molar per second. This reaction is just like me. It gets tired and slows down as it runs. Now that we know how to define and measure the rate of a reaction, we can quantify just how fast a reaction is happening. Whether it's a rapid explosion or the slow decay of a metal bar, understanding rates gives us a precise way to compare speeds.